Linear algebra, it also has a role to play in scientific computing, signal processing, and beyond. So linear algebra do have a role to play in scientific computing, signal processing, and beyond. So linear algebra provides the heavy lifting for complex simulations and data analysis. So we talk about scientific computing, if we talk about scientific computing, so linear algebra plays a role in simulating physical phenomena. So simulating physical phenomena like the weather, fluid dynamics, it requires solving millions of simultaneous linear equations, often using LU or QR decomposition for efficiency. And which are the concepts of linear algebra? So linear algebra, it is used in scientific computing. So when we are simulating physical phenomena like the fluid dynamics, weather, it requires solving millions of simultaneous linear equations. And to solve those millions of simultaneous linear equations, we make use of the concepts of linear algebra like the LU or QR decompositions. Linear algebra also has a role to play in signal processing. So in signal processing, techniques like the fast Fourier transforms, which is also used in Wi-Fi and audio compression, are rooted in linear transformations that convert signals between time and frequency domains. So if we talk about signal processing, in signal processing, converting the time domain into the frequency domain and vice versa is very important. So the fast Fourier transforms, they make use of linear transformations, which is a concept of linear algebra. So linear algebra do play a role in signal processing also. So the fast Fourier transforms, like conversion from a time domain to frequency domain, it makes use of linear transformations. And linear algebra also plays a role in dimensionality reduction. So principal component analysis, it uses eigenvalues and eigenvectors to compress high dimensional data, keeping only the most important features. So the idea is that, let us suppose we have some high dimensional data. Now using the principal component analysis like which makes use of the eigenvalues and the eigenvectors, so we can reduce the dimension. So, so dimensionality reduction we can do using the principal component analysis, which further makes use of eigenvalues and eigenvectors, which is a concept of linear algebra. So now it's very clear to us that, okay, if we talk about scientific computing, signal processing, and beyond, like dimensionality reduction, linear algebra plays a role. In scientific computing, like if we are simulating physical processes, it involves solving millions of simultaneous linear equations. We make use of the concepts of linear algebra like the LU or the QR decompositions. In signal processing, we do the conversion of the time domain to the frequency domain. We make use of something called as fast Fourier transforms. It uses linear transformations, which is a part of linear algebra. And also in dimensional reduction, we make use of principal component analysis, which uses eigenvalues and eigenvectors to compress high dimensional data into important features. So this eigenvalues and eigenvectors is a concept of linear algebra.